Here in example 2, we're going to be finding a numerical integral, and again we're going to be using the graphing calculator to do this. Use the nint, that's just the key on your calculator, to find the area of the region R enclosed between the x-axis and the graph of y equals 1 over x from x equals 1 to x equals 4. Alright, so if we were to write this integral out, our lower bound is 1, our upper bound is 4, our function is 1 over x, and we remember, put a dx at the end. On the calculator, you're going to hit the math key. You're going to go all the way down to number 9, F-N-I-N-T. Alright, so it's a little bit different than the 83. Okay, lower bound is 1, upper bound is 4, and then we're going to type in 1 divided by x, which is our function, and then here you put an x, whatever the variable is, and hit enter. Alright, and so there's your answer. The area underneath the curve of 1 over x between x equals 1 and x equals 4 is 1.386. Now, if you have the TI-83 calculator, you got to do things a little bit differently. And here's what you need to do. So you'd go ahead and you'd hit math. So write this out. You're going to hit math. And then you're going to hit the nint key or the FNINT key. Alright, and then what shows up is this. Okay, and what you're going to have to do is you're going to have to put the function in first, 1 divided by x, and you're going to have to remember this order. So it's function, followed by a comma, and then your variable, followed by a comma, then your lower bound, followed by a comma, and then your upper bound. And then you hit enter and get your answer. Alright, so you got to memorize that order, which stinks. But it still beats having to do it by hand. Okay, number 3, example 3. So here we're going to find distance traveled. So an automobile is driven at a variable rate along a test track for 2 hours, so that its velocity at any time, and the time t is defined between 0 and 2, is given by v of t equals 30 plus 10 sine of 6t miles per hour. How far does the automobile travel during the 2-hour test? Let's set up and write our integral. Alright, how do we know it's an integral that we're going to be using to solve this problem? Integrals help solve distance traveled problems. Okay, that's very important. Alright, derivatives help us find instantaneous velocity problems. Integrals, distance traveled. So our integral, we're looking at an interval between 0 and 2 hours. So there's our upper and lower bound. There we go. Our function is 30 plus 10 sine of 6t, and then dt, so our variable's t. We are going to use our calculator. So we're going to hit math, number 9. Our lower bound is 0. Our upper is 2. Our function. What is the function again? 30 plus 10 sine of 6t, but instead of t we have to put x. Our variable has to always be x on the calculator, and then dx. And hit enter. And there you have it. Alright, so if we interpret the answer here, we conclude that the automobile travels 60.26 miles. Okay, in example 4, finding derivatives from data. So table 10.6 shows the height in feet of a falling ball above ground level as measured by a motion detector at time intervals of 0.04 seconds. Part A, estimate the instantaneous speed of the ball at t equals 0.2 seconds. So the first thing we want to do is get our calculator out. You're going to go to Stat, Edit, and you're going to type in to your L1 list the time, and then the position in feet, that's going into your L2. All right, so you may have to pause this video, take a moment, and do that. Okay, so once you have that in, you're going to go ahead and hit second and the mode key, and you're going to go to your window. Alright, and set the x minimum to 0, the x maximum to 1, the x scale 0.1, and then the y minimum will be -2, the y max will be 10, and the y scale will be 1. Alright, now second, y equals, go ahead and we want to scatter plot here. So make sure that's turned on. And then hit graph. Alright. And so you can see here that this looks like a quadratic model that we're going to be using. So we want to find the quadratic regression. So to do that, you're going to hit Stat, Calc, and then you're going to scroll down to number 5 where it says Quad Reg. Alright, so L1 and L2, we are good. Calculate. So there's our quadratic regression, and what we want to do now is put that into our y equals. So go to the y equals, and then we're going to go to vars, down to statistics, over to equation, and then hit enter. And your regression equation now is in your y1, so when you hit graph, the curve runs through your points. So that would indicate an amazing fit. Okay, now once all that is in place, it's time to solve part A. So A says estimate the instantaneous speed of the ball at t equaling 0.2 seconds. Alright, so instantaneous speeds, instantaneous velocity. We're using derivatives. We're going to use a derivative to find this. Alright, so if we were to write this, we would want to find f prime of 0.2, the instantaneous velocity at t equaling 0.2 seconds. And so our function, we found that is now stored into our y1. Okay, so what you can do now is you can go back to your graph and you can hit second, the trace key, and you can scroll down to dy dx and hit enter, and then a cursor will show up, and we want to find the instantaneous velocity at approximately 0.2 seconds. So you can estimate it this way. So I'm just taking the cursor and I'm moving it till I get approximately x equals 0.2. And then I would hit enter. And so you can see the instantaneous velocity here. It would be negative 14.74, and that would be approximately feet per second at t equaling 0.2. Okay, so that's one way. All right, that's an approximate. What we could also do to get the exact is go ahead and use your math key. This is what we did in example 1. Scroll down to n deriv, hit enter. Alright, so your t would have to be x. Okay, and here's where we are typing in our function. And so we have that stored already. So you're going to go to vars, down to stats, equation. Okay, put the regression equation in. And then your x equaling, so we want to find the instantaneous velocity at 0.2 and hit enter. Alright, and there you have it. So again, approximately the speed's about negative 14.585 feet per second at t equaling 0.2. Okay, so actually what we ended up doing is we did not answer A. We didn't, to estimate the instantaneous, for part A it said to estimate, so that would require us to have done it by hand. We did not do that. So what we did was parts B and C. We drew a scatter plot of the data. We used the we got a quadratic regression to model the height. We found all that. And then we use the n-dir to approximate s prime of 0.2. Alright, so I know I said that we were completing A. We were not. We weren't estimating. We were actually finding the instantaneous velocity. That was not an approximation which we got. Alright, so this concludes 10.4, and I'll be posting your homework to have completed here in a bit.